One young man.
Noise.
Good is correct. Yes, good morning, dear viewers. Hoping that you came. Welcome to today's session. Still, the name and by the name is I'm going to actually take you through. So we are still looking at the quantity of heat. So far so good. In the beginning, we looked at how to calculate quantity of heat supplied, and then yesterday we were looking at the different methods of looking at for the specific heat capacity of the substance. So yesterday we actually concentrated on the method of mixtures. In the beginning of the lesson, that was on Monday, we actually looked at the electrical method for determining the specific heat capacity of a substance. I want to give you a recap. Yesterday I told you that under the method of mixtures, when you heat something, a substance, it could be a solid, it could be water. When you heat a substance, when it is very hot, and then you take it and drop it in a cold substance, the heat of this substance will be lost to the cold substance. And then if this cold substance is also in some other container, which could be an aluminum container, copper container, any, this heat will be lost to this substance in the container, and at the same time the container will also take some heat. So basically, I told you that yesterday that when you heat something like a solid here, and you heat it in hot water, for example, you heat it in hot water, this is the hot water, we say that we shall always consider it to be like θ1. Then you transfer it to cold, like let me say, to cold liquid. It could be also cold, okay, let me just say cold liquid. In that case, if you bring this hot substance now here, now this one will form some other mixture. Will form some other mixture, and this mixture shall form the mixture here. It will be mixture now. This is the cold. Now the resultant, okay, the cold liquid before you bring in the hot substance is at this cold temperature, like you can see. Here I'm going to say that the cold liquid at temperature θ2. Then this hot water, or if I have this solid and I put it in hot water, or I boil it in hot water, and then I quickly transfer it into cold liquid. This is at temperature θ1, this is at temperature θ2, then we shall form a mixture which is going to be at θ3. I told you to get the relationship between these ones so much. This one is at a very high temperature, this one is at a very low temperature. Now the mixture is going to be of temperature θ3, but this temperature θ3 is higher than θ2, but at the same time θ3 is less than what? So θ1 is higher. And that's what we actually talked about yesterday, that θ1 is higher than θ3, but at the same time θ3 is higher than θ2. Those that will fail to understand the method of mixtures will just be because of that. So actually, I want us to look at one more example about the method of mixtures, and then we proceed. In today's session, we are actually going to concentrate on what we call latent heat. Latent heat is heat for change of state. When a substance changes state, like from solid to liquid or from liquid to vapor, there is that special heat that is absorbed at that point. That heat is what we call latent heat, as we are going to see. But before we go to the latent heat, I want to first of all take you through this example. I want to take you through this example, and then some of you may not be here in me very well. Let me try to put the sound enhancement, and you try to hear me very well. So now to those people that are not hearing me very well, I think now you may hear me, you can be hearing me very well. So, now, there is a question that we were supposed to look at. That question that is going to also help you to grasp this. Okay? This question is going to help you grasp this. What we talked about yesterday, they are saying that hot water of mass 0.4 kilograms at 100 degrees Celsius is poured into a calorimeter of mass 0.3 kilograms. And then and the specific capacity of this calorimeter was 400 joules per kilogram per Kelvin. They are saying that this calorimeter was containing a liquid of 0.2 kilograms at a temperature of 10 degrees Celsius. Now they are saying that the final temperature of the mixture is 40. They now want us to determine the specific capacity of this liquid. Here, it may not only be a case of bringing a hot solid to a liquid. Now here we are using hot water. We are now bringing hot water to some other liquid. You realize that now the hot water, once brought to this liquid, of course the heat is going to be lost from the hot water to this liquid. So that is the question. I'm not going to write it on the board because you already have it in the notes. Those that may not be having this, you can follow the audio and know the question will come out well. But according to what is being given there, we have what we call the mass of water. The mass of water is 0.4 kilograms, and then we have this is the mass of the hot water. We have the mass of the liquid at 0.2 kilograms, and then we have the temperature. The theta 1 is 100 degrees Celsius. Then the mass of the calorimeter is 0.3 kilograms, and then the specific capacity of this calorimeter is 400 joules per kilogram per Kelvin, as you can see. The mass of the liquid is there. Theta 2, which is the temperature of the liquid before you bring the hot water, it is 10, and the theta 3, which is the temperature of the mixture after you put the hot water into this liquid. The temperature theta 3 is that. You realize that the only thing we do not have is the specific capacity of this liquid. However, like I told you, that because you are bringing this hot water to now a liquid that is placed in a calorimeter, so we shall say that heat lost by hot water, heat lost by hot water, is going to be equal to heat gained by liquid. Is going to be equal to heat gained by liquid plus the heat gained by the copper calorimeter. Heat gained by copper calorimeter. There are some people that may have not understood this. So heat lost by this hot water is equal to heat gained by the liquid. But we are also adding on the heat gained by the calorimeter, because I told you that if a liquid is in a calorimeter, this heat that is lost by a hot substance may not only go to the liquid, but even the container. When you're heating something like on a saucepan, the saucepan will gain heat, and even what you're cooking with that is within the saucepan will also gain the heat. So this is the situation we are looking at here. Now here I'm going to say MC delta theta. This is also MC delta theta. This is also MC delta theta. That is how much of heat supplied in any case. However, now that this is hot water, allow me to use H here to represent hot water, and even so mass of hot water, specific capacity of hot water. The temperature change we are going to see. Then this one is the liquid, and we shall use mass of liquid. Even here, specific capacity of the liquid. Now here we shall use mass of copper calorimeter, specific capacity of the copper calorimeter. This question is interested in Cl. When you look at whatever has been given, it is only Cl that we do not have. Maybe the other thing that confuses you, the temperature change. This temperature change you see, for the purpose of hot water, it was originally at this temperature. So we shall say theta 1 minus, after mixing this hot water into the liquid, there was some other temperature which was final, and we shall call it theta 3. So here we shall have that. Then here, the cold liquid, this liquid was originally at this temperature 10 degrees Celsius, and we called it theta 2. But because you brought a hot substance which was at 100, when you mixed, the resultant temperature was 40. So in this case, when we are getting temperature change here, we shall now use that theta 3 minus the theta 2. And then lastly, because this liquid, whatever happens to this liquid is what happens to the calorimeter, because they are together. So in this case, we shall have also the temperature change at theta 3 minus theta 2. Friends, if you understand that, you will not find any challenges with the calculations of the what? You will not find any challenges with calculations as far as the method of mixtures is concerned. Now, here, we shall have what we call we shall just substitute. We are going to substitute. The mass is already in kilograms, so we shall just put 0.4. The specific capacity of hot water is the same as for water. And this one, you already know it is 4,200. Whether it's given, whether it's not given. If it's not given, you look on top of the question what will be there. Now, according to the question, our theta 1 was 100 minus theta 3, which is 40. Then we shall have mass of the liquid is 0.2. The specific mass of the liquid is what we are looking for. The temperature change here is going to be 40 minus the 10 plus the mass of the calorimeter is 0.3 kilograms. All the masses were given in kilograms, 0.3. The specific capacity of the copper calorimeter is 400, and the temperature change is still 40 minus 10. In the interest of time, because our lesson today we are aiming at looking at latent heat, I think you may simplify here. When you simplify, you are actually expected to get, if you simplify very well, you're actually expected to get our specific capacity as the CL is equal to 16200 joules per kilogram per Kelvin. That's when you simplify. Let me give a day note for this. Allow me to be at that so that we continue. We go to what they call the latent heat. However, in the last example that is there in your notes, number 7, they are saying that we have a small problem there. They are saying that there was a heater of 15 watts. A 15 watt heating coil is immersed in 0.2 kilograms of water and then switched on for 560 seconds, during which time the temperature rises by, when they say the temperature rises by, that is already a temperature change. And then they are saying that when this water was replaced by some volume of another liquid of mass 0.15 kilograms, the power required for the same time was 8.3. Now they are saying we should calculate the specific capacity of this liquid. That question, I think you can follow. We said that when you use a heater to heat a liquid, just say that heat supplied by the heater is equal to heat gained by the liquid, and that's what is in the notes. So I think you can follow it. I want to begin the latent heat. So that we can work out very well in the latent heat there. So I'm ensuring here with the technical team to see that I start projecting for you the notes, especially those that do not have them, so that at least you can be able to see my notes. But what I'm saying here is that when you use a heater to heat, whether you've heated a solid, whether you're heating a liquid, the heat lost by the heater will equal to the heat gained by the solid. If it is a liquid and it is in a container, like the way you are seeing the copper calorimeter, then heat supplied by heater will be gained by the liquid plus heat gained by the copper calorimeter. That is, if the liquid is in a copper calorimeter. And if this side the heat is being supplied by the heater, we shall say that the heat supplied by heat theta 2 minus theta 1, then plus mass of calorimeter, the what? It will already be the temperature change. So I now want to project my team. With my team, they work that latent heat is heat for change of state. Actually, when we are defining latent heat, we say that latent heat, this is the heat required to change the state of a substance from one state to another without changing temperature. Latent heat occurs at a constant temperature. That is why when the liquid is freezing or when it is melting, that happens at 0 degrees Celsius. When ice is melting, it does so at 0 degrees Celsius. When water is changing from the water state to vapor, it does so at 100 degrees Celsius. 0 degrees Celsius and 100 degrees Celsius, those are fixed temperatures, those are constant temperatures. Maybe at a later stage we shall know why temperatures normally remain constant when there are changes in state. But the heat in this state of changing a state, that heat is what we call what? We call it latent heat. Now this latent heat has two types. We have what we call latent heat of fusion, that is the heat required to change a substance from solid to liquid without at a constant temperature or without changing the temperature. We then also have what we call latent heat of vaporization. Latent heat of vaporization. This one, latent heat of vaporization, is the heat required to change the state of a substance from liquid to vapor, still without change in the temperature. Now, in case this time around we are not talking about any mass. When you bring in an aspect of mass, when you bring in a constant temperature, now there is something that is not clear there. I'm trying to see that I rectify it for you, but we are going to begin with the of course, when a substance is changing state, there is absorption of some heat. There is absorption of some heat. We are going to begin with the latent heat of fusion. I've told you that there are two types. Actually, let me first write for you something here. Latent heat. Heat required to change a state of a substance. Change a state of a substance without change. Without what? Change the temperature. Without changing the temperature. Or at a constant temperature. We are saying that types of latent heat. Types of latent heat, we have two. The types of latent heat, we shall have what we call latent heat. We have latent heat of fusion, latent heat of heat, latent heat of vaporization, latent heat of vaporization, latent heat of fusion, and then latent heat of vaporization. So, hoping we are there. I've tried to project some work on the screen, hoping you can follow. We are saying that when a solid is melting, a solid, latent heat of fusion is absorbed, forces of attraction between these solid molecules, so that they are able to be set free to allow them to move apart, so that they can now do what? They can now change from solid to liquid. Now, when it comes to evaporating a liquid, we have what we call latent heat of vaporization. This latent heat of vaporization, for it is also absorbed to break the intermolecular forces of attraction between the molecules. Intermolecular forces of attraction between the molecules. What's not studied? So, I was still saying, we are going to basically begin with this latent heat of fusion. this begin with the latent heat. We are going to just begin with the latent heat of fusion. Now, the latent heat of fusion, we are saying that this is the heat required to change any mass of a substance from solid to a liquid. That is at a constant temperature. Hoping you can see it on my notes there. I'm trying to project them. Then, that is the latent heat of fusion. We are saying it is the heat required to change any mass of a substance from solid to a liquid at a constant temperature. Now, when we talk about a mass of 1 kilogram, then we shall bring in what they call specific latent heat of fusion. But any change from solid to liquid, that change is what we call fusion. So it is said that is the heat required in that case is latent heat of fusion, and this takes place at a constant temperature. But I've told you that before that melting takes place, this heat absorbed has to break those intermolecular forces of attraction to set the molecules of free, to set the molecules of the liquid free. Now, when we talk about the mass of 1 kilogram, then we bring in what they call specific latent heat. Specific latent heat, we are saying that this is the heat required to raise the specific latent heat of fusion. We are saying that it is the heat required to change 1 kilogram mass of a substance from from solid to liquid at a constant temperature. It is the heat required to change 1 kilogram mass of a substance or of a solid, that is to a liquid at a constant temperature. Now the SI heat is there, it is measured in joules per kilogram, hoping you can see. By formula, we are saying that specific latent heat of fusion is heat over mass. Specific latent heat of fusion is heat over mass. Now, the heat, that one you're seeing as Q, it is, that one you're seeing as theta, it is supposed to be Q. And this is LF. So, what you're seeing there, I'm trying to rectify some of the small mistakes that you may have in your notes there, and try to improve. We are saying that the specific latent heat, specifically latent heat, of fusion, which we are saying it is LF, it is supposed to be heat over M. And actually here we can beautify the formula as Q F. So that formula, this one is what we use in the calculations of latent heat. Q, where Q is the latent heat. Q is equal to the latent heat. This amount latent heat of fusion. Now the other one, the LF, is the specific latent heat of fusion. Hoping you have seen. So try to make that correction. Here in the notes it appears like as if it is a theta, and yet theta we've been using it to mean temperature, but it is Q. Q is the latent heat of fusion, then LF is the specific latent heat of fusion. I've just said that specific latent heat of fusion is the amount of heat required to change 1 kilogram mass of a solid to liquid at a constant temperature. So hopefully we are together there. Now, we are going in for an experiment to determine this, to actually determine this LF. The LF, I've told you, it is what they call the specific latent heat of fusion. I'm trying to predict for you an experiment. We are saying determination of specific latent heat of fusion. The diagram, let's see. The diagram is what's the the diagram, I'm trying to see that in this experiment, the diagram is trying to do what? To miss. The diagram is missing, but I'm trying to draw it for you here. An experiment. To determine the specific latent heat of fusion. I'm going to show you the steps, but I want to show you the diagram that was missing there, so that you may try to include it there. The diagram that was missing, so that you try to include it there. So, so this diagram is here. We get so we are trying to put for you the steps. I'm going to draw for you the diagram there. I'm trying to do what? To put for you the steps here. So this is the experiment. Those are the steps. Determining specific latent heat of fusion. Number one, we shall need to insert in this experiment. We are going to measure mass of a beaker, and then after we shall need to let me first sort out some problems here with my work, and then I'll be coming back, please. Sorry for the interruption of the discussion. So I'm trying to bring for you a well-detailed thing, so that at least you can have it properly managed here. Okay. So I'm trying to sort out the linkages in my work. There are some things that have been lost here, so that the experiment does not come out what? Yeah? It's different. It's talking. It's talking the camera. Camera is good. Live stream is talking. Live stream is continuing. Work I have to test. I'm running a post to bring it, so let's get out to bring this one. Move the camera. Not visible. There's a result of the number. Whatever computer diagrams are the lost. Because I'm really able to be successful. Nze nandi muntu kasita kikopi bw'atyo. Yes, when you have your own carbon, you don't want to do this.
I'll stop streaming. Oh, wonderful. You do the diagram as you explain some aspects. Yep.
Let's have the right time so one next week here. Another chick with the sound. So what we are doing. Now, I wanted so much for you guys to be able to see my notes as I'm trying to explain so that the things come out clear for you, but we are still sorting out some issues here. However, the experiment we are looking at is this one. We get an immersion heater and then we insert it into ice. Ice. These are ice crystals. Then, but before we do all that, we get a beaker, an empty beaker of known mass M1, and then we place it down here. We get an empty beaker of known mass M1, and we place it at the bottom there. Then after, we get ice crystals, and then we pack them into a funnel, like you've seen here. We get ice crystals and put them into a funnel, and then after putting these ice crystals into a funnel, then we insert a heater, an immersion heater. This one is what we call immersion heater. We place the immersion heater into these ice crystals, and then what happens is that when you realize that drops of water have started dripping here constantly, then you switch on this heater. You don't switch on the heater before you start seeing ice melting here. So what you do, you like I've told you, I've said, get a beaker, an empty beaker of known mass M1, and then place it here at the bottom. Then up here you put a funnel. You can support that funnel maybe using a retort stand, anything. Then after you pack that funnel with crystals, ice crystals. When you see that water has started dripping from these pieces of ice constantly, then you insert you insert this heater, and then when you see that water has started dripping constantly, then you put on the heater. You can see that this heater is connected to the battery. Now this is the experiment. We expect that this heater, after heating this ice, the ice is going to melt. The ice is going to melt, and then first we shall say that this ice, because it's going to melt, we shall say that it has absorbed what they call latent heat of fusion. That is the heat that will be required to melt it, so that it becomes what? The water. Then after melting for some time T, we stop the heat, and then we remove the beaker, and we again determine the mass M2 of now this beaker when it is containing the melted ice. This is melted ice. Melted ice is going to be in form of what? Of water. And then at the end of the day we shall say heat supplied by a heater, that is power times time, is equal to the latent heat of fusion, MLF. But this MLF is going to be M2 minus M1. So I want to give you some brief steps here so that for this very experiment, that is the diagram, so that you try to improve the new notes that we gave you. Anything that is missing out, you try to do what? Improve it. So we are saying that a beaker, step number 1, a beaker, an empty beaker, an empty beaker, an empty beaker of mass M1 is placed under a funnel. Then we are saying that the funnel is packed with ice. The funnel is packed with ice. An immersion heater. Of low power P. An immersion heater of low power P is inserted into the ice. An immersion heater of low power P is inserted into the ice. So when this ice now starts, when the ice starts dripping at a constant rate, you see water trying to flow at a constant rate, you switch on the what? The heater. So when the water from the ice, starts dripping continuously, the heater is switched on. So when you see that water has started dripping continuously, you switch on this what? You switch on this heater. Now after some time t, which is going to be time in seconds, you will find that some amount of water will have collected within the what? Within this beaker. So I now want to rub off this diagram, hoping that people have tried to draw it. After time t of what? Melting. After time t of melting, the heater is switched off. Heater is switched off, and the mass M2 of the water, or of the melted ice, together with the beaker is determined. Then after, because this heater is one that has supplied the heat that has been used to melt this ice, we shall say that heat supplied by heater, is equal to heat, latent heat is equal to the latent heat of fusion. It is this heat that will have been responsible for this. Now, I was saying that you get an empty beaker of mass M1. Now here, when we are at the end of the experiment, when we get the beaker and we measure its mass again together with this melted ice, that mass we shall call it M2. Why are we measuring it? So that when we get the difference between M2 and M1, that mass we shall get will be the mass of the melted ice. The mass of the melted ice. Now at the end of the experiment, you've seen that in this experiment, we need to get the mass of the melted ice, which you've seen. Then we need to also determine the power supplied by the heater. That means we need to heat. This heater needs to heat, to supply heat for a long time T. And this heat is what we use for melting, which the heat we call latent heat. So at the end of the experiment, we say that heat supplied by the heater, which is going to be power times time, is going to be latent heat of fusion. And I've already shown you that latent heat of fusion is MLF. Latent heat of fusion is MLF. But this M is the difference between the M1 and M2. Actually, M is M2 minus M1. So that's what I want to show you here. Heat supplied by the heater is going to be power times T, which is equal to M. This time around we are going to say the M2 minus M1. That difference then LF. Remember, our interest is in getting LF. Maybe before that, let me show you that it is MLF, but this M is the M2 minus M1. So, and then here we can make LF the subject of the formula. LF the subject of the formula. So that we have PT over M2 minus M1. So that is the specific latent heat of fusion. Once again, I want to inform you that specific latent heat of fusion is the heat required to change 1 kilogram mass of a liquid, of a solid, into liquid at a constant temperature. Why is this happening at a constant temperature? It is simply because this heat that is supplied at that point of change of state, this heat is actually used to break the intermolecular forces of attraction between the molecules of the substance, to set them free or to make them free and ready for change of what? And ready for change of state. That is it. So that is why you see that much as the heater will be supplying the heat, the temperature will remain constant. The heat is instead used to, the heat that would raise the temperature is instead used to break the intermolecular forces of attraction between the substances. Now, I want to take you to the latent heat of fusion. I want to take you to latent heat of fusion, and rather to latent heat of vaporization. Latent heat of vaporization. Now, this latent heat of vaporization, I've embarked on writing this because you need to also make improvements there. Where you find errors, some diagrams are missing, you try to improve. Now, latent heat of vaporization, we are saying that this is the heat required. This is the heat required. This is the heat required to change the state of the substance, to change the substance, to change substance from liquid to vapor, from liquid to vapor at a constant temperature. At a constant temperature. This is the heat required to change a substance from liquid to vapor at a constant temperature. So, you can see, now this is the latent heat of vaporization. Now we have what we call specific latent heat of vaporization. The specific latent heat of vaporization. Now when we bring the word specific latent heat of vaporization. It is the same as that definition I've given above there. The difference here is that we talk about 1 kilogram mass of a liquid. That's why I brought in this one, which is specific. So we shall say that this is the heat. This is the heat required to change. Just bring it 1 kilogram mass of liquid. 1 kilogram mass of liquid from 1 kilogram mass of liquid to vapor at a constant temperature. So that one, that is the specific latent heat of vaporization. The specific latent heat of vaporization, and they are the same definitions, but only that here we just bring in the aspect of 1 kilogram. Now SI unit, like it is the same as the one for specific latent heat of fusion. Even this one is joules per kilogram. Then the formula, the other side, when we were talking about latent heat of fusion, we said that latent heat of fusion Q is mLF. Latent heat of fusion Q is mLF. And then this time around, when we are talking about latent heat of vaporization, we shall say latent heat of vaporization Q is mLV. Latent heat of vaporization Q is mLV. So latent heat of vaporization Q is equal to mLV. Of course, where LV is equal to the specific latent heat of vaporization. Specific latent heat of vaporization. Now, that is the formula we use. Now we are going to look at the experiment. Hoping you see the experiment on your screen. This experiment is meant actually to help us get LV. Like we underweight in the experiment to get LF. Here we have the experiment. This time around, I think this one you see it clear. That is the diagram. In this diagram, instead of using a heater of no power, we've just inserted the heater and we've connected the voltage across it, and then an ammeter. The role of the voltage, we've connected the voltmeter across it so that we can see the voltage, and an ammeter. The ammeter is going to help us see the current. So, and these two, once combined, the ammeter reading and then the voltmeter reading, the ammeter reading will be the I, and then the voltmeter reading will be the V, and these are the ones we shall use to calculate the power. Now, in this experiment, to determine LV, the method of work is most likely actually to remain the same. Only that, this time around, we are using a liquid. So what we do, they are saying that a liquid is poured in a beaker, and the mass M1 of the beaker is noted. The liquid is poured in a beaker, and the mass M1 of the beaker is noted. Hoping you can see on that diagram. That is the weighing machine. Then the beaker is placed on top of the weighing balance. They are saying that the beaker is placed on top of the weighing balance, and then the heater is totally inserted, immersed into the liquid. The heater is totally immersed into the liquid. Why the heater is inserted into the liquid? We want to heat this liquid so that it reaches the level, of actually evaporation. So that it reaches the level of evaporation. Now, what happens is that we shall say that the heater is switched on until the liquid until the liquid starts boiling. The heater is switched on until the liquid starts what? Boiling. The heater is switched on until the liquid starts here. So we are heating this so that the heater is switched on and left until the liquid starts what? Boiling. Now when the liquid starts boiling, the stop clock is also started. Why? We are starting the stop clock to see that we can determine the time for which this boiling takes place. You know, when boiling begins, that means that the liquid has started from changing from the vapor state to from the liquid state to the vapor state. So our interest is actually determining that time t that it will take to form some amount of vapor. So what happens when the liquid is now boiling is allowed to continue for some time t. Boiling is allowed to continue for some time t, and then finally we shall get the reading on the weighing balance. The reading M2 on the weighing balance is actually good. Remember, before the boiling began, actually we had the liquid. We had the mass of the liquid M1. We are reading it directly on the weighing balance. You see that mass that you read in the beginning, that will be the mass of the liquid together with the container, because this container is placed on the weighing balance. So you can easily see the reading M1. You can easily see the reading M1. Now after you allow boiling to take place for some time, I'm trying to ensure that this work comes back onto your screen there so that you see it. When you allow this boiling to take place, as boiling takes place, evaporation process also takes place. Evaporation process takes place, and as the evaporation takes place, you are going to some liquid is going to be changing into vapor state. That means that the mass of this liquid will be reducing. So we shall need to read the weighing balance at the end of the heating process. When we allow boiling to take place for some time t, we shall need to get the mass. Now we are saying that if M2 is the mass that remains, mass of the liquid together with the container, because you got this and placed it onto what? You placed it onto weighing balance. So if at all I'm trying to show you here the work. It is just close here. That is that diagram is there. So hoping you can see there. We are saying that boiling is allowed to continue for some time t, and then the reading of the weighing balance M2 is noted. Now when sufficient liquid has vaporized, so the difference in the weighing balance M, which is equal to M1 minus M2, that difference M is going to be representing the mass of the vapor. We're actually looking at the stages of the treatment of the results. And now the ammeter reading I, we read it. We read the ammeter reading I, and then the voltmeter reading V. The voltmeter reading V. After reading the ammeter reading I and the voltmeter reading V, then we shall say heat supplied by heater. Heat supplied by heater. Heat supplied by heater, which we are going to say it's this time around we are going to use VIT. VIT is equal to MLV. MLV, and when I make LV the subject, it is going to be VIT over M. LV is going to be VIT over M, which you can see. But only that in your books or in the notes that we gave you, this LV, we wrote it as L. You can make it L what? LV. Friends, before I summarize the lesson, I want to go through one example, actually two examples. You already see them there on the screen. We are saying that ice has a mass of 3 kilograms. We are saying that calculate the heat required to melt it at 0 degrees Celsius. That is the heat at 0 degrees Celsius, means at that constant temperature. In the brackets, they have given us the specific latent heat of fusion at 3.36 times 10 to the power 5 joules per kilogram. Now here, because we are talking about latent heat of fusion, you will say Q is equal to mLF. Still in your notes there, I wrote it as L just, but it is supposed to be mLF. That L will make it mLF, and because we already have our mass in kilograms, we just multiply 3 times 3.36. So that amount of heat Q we got, that is what we call the latent heat of fusion. Then when we go to that next number, I think you can see it. They are saying that find the heat required to change 2 kilograms of ice at 0 degrees Celsius into water at 50 degrees Celsius. Now you realize that here we have a task to heat ice at 0 and we take it to water at 50. Now these calculations you will also understand them. They are a bit technical, but you will understand them. Now for you to be able to heat ice which is at 0 degrees Celsius, to take it to water at 50 degrees Celsius, there are some stages that do take place. Number one, ice has to first change from ice to water. And the heat required to change ice from ice to water, that is what we call the latent heat of fusion. Rather, that is what we call the latent heat of fusion, and that is what we call mLF. Now, after you've heated this ice and it has become water, that thing was well elaborated for you there on the diagram. Ice at 0, we shall supply heat which is mLF. Now, after it will become water at 0, and then that water at 0 is what you're going to heat up to water at 50. That plus is supposed to be an arrow. That plus is supposed to be water so we are saying that heat in this case, first we need to have ice at 0 degrees Celsius, and then that ice becomes water. So the water at 0 degrees Celsius. The water at 0 degrees Celsius. Now this water is now what you are heating, and it becomes what? Water at 50. We are in the summative stages of this lesson. Water at now the heat here is MC delta theta, because there is change in temperature. The heat here where we don't have change in temperature is mLF. So here the total heat here, the total heat supply, total heat required, of course it's going to be mLF plus the MC delta theta. That is basically how it was supposed to be. The delta theta is going to be a change in temperature from 50 degrees Celsius minus 0 degrees Celsius. I think everything is there because it's water. Specific capacity of water is 4200. So here we shall have our mass of this water. The very water, the 2 kilograms of the ice are the ones that are becoming 2 kilograms of what? Of water. Please, I want you to make some correction there. The mass this here is supposed to be 2 times the latent heat of fusion, which is the specific latent heat of fusion, which is 3.36 times 10 to the power 5. That one was supposed to be 2, and then plus the same mass of ice is the same mass that has become what? Water, and then it will be 2 times 4250 minus 0. So friends, I think that is enough work for today. We shall look at more harder tasks, inshallah. Try to read through that work, try to make the necessary corrections that you find in these discussions. May God bless you. In case you have any questions, you can always feel free to ask them. But I've told you that there are 2 types of latent heat. Latent heat is heat for change of state. There are 2 types of latent heat of fusion, and then latent heat of vaporization. Fusion means changing from solid to liquid. Vaporization means changing from liquid to vapor. When you bring in the word specific, that means you are talking about mass of 1 kilogram. Specific latent heat of fusion, that means you're talking about mass of 1 kilograms. So the heat required to change 1 kilogram of solid to liquid, the constant temperature is what we call specific latent heat of fusion. We even seen the experiments. Try to read it through, and while you're reading the experiments, make sure that you practice them on paper also. Don't just read them after, practice on paper, and then try to see whether you can recall them and rewrite them without looking anywhere. You will see that you will improve. Otherwise, have a nice time. May God bless you. In case of questions, you will send them.